Okay, so we represent the crystal planes. We represent crystal plane by curve bracket, and inside the curve bracket we write integers h, k, l, and these integers are actually called as Miller indices. Okay, how to find Miller indices? Yes, we discussed many examples. First find out the intercepts. Okay, first find out the intercepts, then take the reciprocal, clear the fraction. Okay, if negative number exists, put bar 1 above that. Okay, so we discussed many examples. Now I'll do some more example. Take down. Yeah, I'll give a plane. You try to find out what is the Miller indices for this plane. Okay, I'll give a plane. Yes, try to find out Miller indices for this plane. So this is the x-axis, and this is the y, and this is the z. Okay, and this is half, this is half, and this is actually 1 unit. Yes, what is the Miller indices for this plane that is shown here? I'll show you how to do that. First find the intercept. So this plane makes intercept along x-axis at 1 unit length. So intercept, first I'll write the intercepts. These are the intercepts. Right, intercepts first along x. X intercept is 1 unit length, and y intercept is half unit length, 1/2, and z-axis intercept is also half. So these are the intercepts. Then what is the second step? Take the reciprocal. Take the reciprocal. So reciprocal of 1 is 1 only. Reciprocal of 1/2 is 2. Reciprocal of 1/2 is again 2. So we get, we obtain directly integers. There is no fractions. Therefore, the Miller indices for this plane is 1, 2, 2 plane. Okay, take down. I'll give intercepts. Okay, some plane in a crystal makes these intercepts along x, y, and z axis. Okay, I'll give the intercepts. Intercepts, right? X intercept is 3a, y intercept is 5a, 5b, I'm sorry, 5b, and z-axis intercept is minus 2c. 3a, 5b, minus 2c, where a, b, c, they are all unit lengths along x, y, z axis. This is a is unit length along x, b is unit length along y axis, then c is the unit length along z axis. Okay, now I have given the intercepts. You try to find out what is the Miller indices correspond to this plane. Okay, take two. First, remove the unit vectors here, unit lengths, that is a, b, c. So you just write the numbers 3, 5, minus 2. 3, 5, minus 2 will form the Weiss indice, you know very well. This is called Weiss indices. Now take the reciprocal. 1 over 3, 1 over 5, minus 1 over 2. Okay, we took the reciprocal, but now we got fractions. We have to clear the fraction. Okay, so how to clear the fraction? Just multiply all these numbers and take the LCM actually. So for these three numbers, LCM is 5 into 3, 15. 15 into 2, 30. 30 is the LCM. So multiply everything by 30. Multiply everything by 30. So what we get? 30 by 3 is 10. 30 by 5, 6. 30 by 2, 15. So Miller indices for this plane is 10, 6, 15. We have minus sign here. So put bar 15. 10, 6, bar 15 is the Miller indices for this plane. Okay, take note. Now I'll do this problem. Listen. First step is remove A, B, C. Write the coefficients minus 2, minus 1 by 2, minus 3. Okay. Now take the reciprocal. Minus 1 by 2. 1 by 2 reciprocal is 2. This is minus 1 by 3. Now I have 2 here and 3 here. We need to remove the fraction. 3 into 2 is 6. So multiply throughout by 6. You will get minus 3, minus 12, minus 2. Okay. So the Miller indices are 3 bar, 12 bar and 2 bar. Take note. Yeah. How to find Miller indices for hexagonal crystals or simple hexagonal crystals. Okay, let me write here. So simple hexagonal crystals. For this, we use Miller indices called Miller-Bravais indices. It's called Miller-Bravais indices, which involves 4 values. Okay, H, K, I, L. Miller indices involve only 3, H, K, L. Miller-Bravais indices involves 4 integers, H, K, I, L. And here one important condition here is H plus K plus I should be 0. This is very important condition. Take note. Now I will show you how to find the Miller-Bravais indices for hexagonal crystals. Okay, so what to do? Listen. First I will take the basal plane. This is called the basal plane for the hexagonal initial basal plane. Now I will take this axis, then this axis, then this axis. Okay, I will take this as A1, this as A2 and this as A3 axis, and we have a perpendicular axis. See, this axis is perpendicular to the basal plane. I will take this as A4. So we have 4 axes now. Now let me take some plane here. Listen. And for that plane we will find out what is the Miller indices. Okay, suppose assume that a plane passing through these corners. Okay, it passes through this corner, and the plane is like this. Okay, the plane is like this. What is the Miller-Bravais indices for this plane? How to find out? Okay, take note. Then how to work out? See, it cuts the A1 axis in unit length. Okay, in unit length. So I'll take that unit length as 1. It cuts the A2 axis in unit length. So 1. Okay, 1, 1. Then it cuts the A3 axis. Listen. This is actually positive side for A3, and this is the negative side, corresponding negative side. Okay, this is minus A3. So this plane cuts the A3 axis in the negative side, but not full length, off length. So it is minus 1 by 2. Minus 1 by 2 along A3 axis, but it is parallel to A4. Parallel to A4, so infinity. Intercept is infinity. Now take the reciprocal. So these are the intercepts. Now you take the reciprocal. Reciprocal for 1 is 1. Reciprocal for 1 again 1. Minus 1 by 2 reciprocal is minus 2. Reciprocal of 1 by infinity is 0. Okay, therefore the Miller-Bravais indices for this plane is 1 1 bar 2 0. Take note. It's very simple. Example number 2. The origin, this is A1 axis, this is A2 axis, A2, and this is A3, and the perpendicular axis is A4. Okay, now I'll give some plane here. Say for example, I'll take a plane here, this plane. Okay, what is the Miller indices for this plane? I have a plane here which is parallel to A4 again. Find the Miller-Bravais indices for this plane. This plane passed through this corner and this corner. Can anyone tell me what is the intercepts that this plane made with A1, A2, A4? What are the intercepts? Let me write here. Listen, now I have drawn a basal plane of hexagonal unit cell. Now I'll give you a plane. You try to find out what is the Miller indices. Okay, I'll take, listen, a plane passing through these 2 points. Find the Miller indices for this plane. First step is you need to identify the intercepts. Okay, how this plane makes intercepts with A1, A2 and A3, then A4. Yes, anyone tell me? So this plane is parallel to A1 axis, so intercept is infinity. This plane cuts the A2 axis at unit length, so put 1. Then this plane cuts the A3 axis in the opposite direction, so this is minus A3 actually, in the opposite direction by 1 unit length, so put minus 1. And this plane is parallel to the A4 axis, so intercept is infinity. Then the next step is take the reciprocal. 1 by infinity, 1 by 1 is 1, 1 by minus 1 by 1 is 1, 1 by infinity. Take the reciprocal. Then what is the next step? Okay, 1 by infinity is 0, 1 by 1 is 1, minus 1 by 1 minus 1, 1 by infinity 0. So what is the Miller-Bravais indices? 0, 1, bar 1, 0. This is the Miller-Bravais indices for this particular plane. Okay, take notes. The next question. So I have taken the simple hexagonal unit cell where I have fixed the axis here. This is my origin. This is axis A1, this is axis A2, and this is axis A3. A4 is perpendicular to this basal plane. Now I'll give this plane. Okay, you take this plane. What is the Miller-Bravais indices for this plane? Okay, how to find out? So these are the intercepts, right? This plane is parallel to A1, parallel to A2, and parallel to A3. It cuts the A4 axis at unit length. Since it is parallel to A1, the intercept is infinity, and parallel to A2, so intercept infinity, parallel to A3, so intercept is infinity, but it cuts the A4 axis at unit length, so intercept is 1. Now next step is take the reciprocal. 1 by infinity, 1 by infinity, 1 by infinity, 1 by 1. 1 by infinity is 0, 0, 0, 1 by 1 is 1. Okay, therefore the Miller-Bravais indices for this plane is 0, 0, 1 plane. Okay, take two. How to find the angle between crystal planes? Okay, before going to that, listen carefully. Suppose I'll give some plane like this 1, 1, 1. What does it indicate? It cuts the x-axis, y-axis and z-axis at unit length. Suppose if I give a plane 2, 2, 2, what does this indicate? Can anyone tell me what does this indicate? 2, 2, 2 means?
Cut off, sir.
It cuts the x-axis at half length, y-axis at half unit length and Z also half unit length. Okay. Remember, these two planes are actually parallel. They are parallel planes but not equivalent. They are parallel planes because size of this triangle and size of this triangle, or area covered by this triangle and area covered by this triangle, are not equal in a given unit cell. Therefore, they are not equivalent but parallel planes. If they are parallel, we cannot find the angle. Okay, so keep that point in mind. Now, how to find the angle between two planes? Suppose I'll give Miller indices for one plane, H1, K1, L1, and Miller indices for another plane, H2, K2, L2. Okay, I have given Miller indices for plane 1 and Miller indices for the crystal plane 2. Now, what is the angle between these two? To find the angle, what to do? This is the formula. Remember, cos theta equal to H1 into H2 plus K1 into K2 plus L1 into L2 divided by square root of H1 square plus K1 square plus L1 square into square root of H2 square plus K2 square plus L2 square. Take note. This is the formula we use to find the angle between two crystal planes. If their Miller indices are available, we can find out. Okay, take note. So let me show you how to use this formula. I have taken two planes here, 1 0 0 plane and 0 1 0 plane. What is the angle between these two? So you know very well, cos theta equal to, okay, this is H1, this is K1 and this is L1. This is H2, K2, L2. Okay, let me write here H1, K1, L1, and these values are H2, K2, L2. Now what you have to do? Multiply H1 and H2. So 1 into 0 is 0 plus H1 into H2. So 1 into 0 is 0 plus K1 into K2, 0 into 1, 0 plus L1 into L2, that is also 0. Now, since the numerator is 0, okay, let me check the denominator. See, in denominator we have, see, H1 square plus K1 square, H1. H1 is 1, 1 square is 1, so I'll get root 1. K1, L1 are 0, so you need not worry about them. Into, then here H2 is 0, K2 is 1, therefore I'll get square root of 1 here because K2 square is 1, remaining number becomes 0. So, listen here, root 1 into root 1 is 1, but in the numerator I have 0, 0 by 1, root 1 into root 1 is 0. Anything by, listen, 0 by anything is 0. 0 by anything is 0. Okay. Which angle will give cos theta equal 0 degree? Anyone tell me? Yes, you are right. Yes, theta equal to 90 degree, okay, is the angle between the two planes. Listen, I'll just show you what are these planes actually. Listen, I'll take a cube, I'll show you whether this 90 degree is correct or not. You can check it actually. Observe carefully. This is the x-axis and this is y and this is z-axis. First, this plane I'll take. It cuts the x-axis at 1 unit length. Yeah, okay, and it is parallel to y and parallel to z. Therefore, this is the plane. This is the plane. Okay. And what about the second plane? It cuts the y-axis at unit length. Okay, but it is parallel to x and z. So it is parallel to x and z. So this is supposed to be the plane. What is the angle between these two planes? Can anyone tell me? What is this angle?
Same 90 degrees, sir.
90 degree, yes, our answer is correct. Okay, take note. Find the angle between these two planes. Okay. So this is H1, K1, L1 and these are H2, K2 and L2. What is the angle? Cos theta equal to, yes, cos theta equal to H1 into H2 is 2, K1 into K2 also 2, L1 into L2 also 2. Then square root
0
of
degree as
H1 square. Yes, Manu, you're right. H1 square plus K1 square plus L1 square. So 1 square plus 1 square plus 1 square. 1 square plus 1 square plus 1 square. You will get root 3 into square root of H2 square. 2 square plus 2 square plus 2 square. Okay. So numerator we have 6. Denominator this is root 3. And here 2 square is 4. 4 plus 4 8. 8 plus 4 12. So square root of 12. Okay. You can write this as 6 by root 3 into root 4. You can separate 12, root 12 as root 3 into root 4. Root 3 into root 3 become 3. So 6 by 3 into root 4. 1 3s are 3, 2 3s are 6. So, and root 4 is 2. Root 4 is 2, so 2 by 2 is 1, correct? I am getting cos theta equal to 1. Okay, which theta angle will give cos theta as 1? So, we get theta is equal to 0 degree. Okay, theta 0 degree implies that the two planes are parallel actually. Okay, so 1 1 1 plane and 2 2 2 planes are parallel planes, right? Take 2. So, our next task is to find the interplanar spacing. Okay, to understand what is interplanar spacing and how to find interplanar spacing between equivalent and parallel planes. So, we are going to find interplanar spacing, right? Interplanar spacing between adjacent, parallel and equivalent planes. This is very important. Equivalent planes. Okay, if one plane is 1 1 1, the next parallel plane should also be 1 1 1. Okay, now we are going to find out what is the interplanar distance between 1 1 1 planes, adjacent 1 1 1 planes, or adjacent 2 2 2 planes, like that. Okay, so we are going to find out interplanar spacing between adjacent, parallel and equivalent planes. Okay, right. I have told you, so this is also parallel. See, 1 1 1, 2 2 2, they are all also parallel, but they are not equivalent. They are not equivalent. So we are not going to find out the interplanar distance between these two planes. We are going to find out interplanar distance between parallel and equivalent planes or similar planes. Okay, instead of equivalent, we can also use the word similar planes. Similar planes. That's the right word actually speaking. Right? Now, yes, listen. Actually, we can derive this mathematically, but I am not going to do that. Mathematical derivation is possible, but I am not going to do that. I am going to give you the general formula first. What is the general formula? Formula to find the distance between adjacent, parallel, similar planes. Okay, general formula. 1 by b square corresponding to HKL plane is equal to 1 by v square, where v is the volume of the unit cell, v square into this is the formula. Remember the formula, it's very easy actually, h square. So you have HKL, right? So start with h square, b square c square sin square alpha. The formula is somewhat lengthy, okay, plus then after h you start with k square, bc, here you have taken bc, next you take ca, c square a square sin square beta, plus I don't have space here, so let me write here, let me continue here, l square a square b square sin square gamma plus 2hk a b c square into cos alpha. This is a lengthy formula actually. Cos alpha, you need not memorize this, it's not necessary at all, minus cos gamma, and it continues, actually it continues, plus, we don't have space here, so let me write here, 2kl a square into bc into cos beta cos gamma minus cos alpha. We can actually derive, method is available, but it's not necessary for the preparation of competitive examinations, so I am not going to do that. Plus 2lh a b square c into cos gamma cos alpha minus cos beta. This is the formula to find the interplanar distance between adjacent, parallel and similar planes. This is the right word, actually, similar planes. Okay, but here what is actually V? V is the volume. Okay, and what is the general formula for volume? General formula for volume is equal to a square b square c square. A, B, C are nothing but unit length along x-axis, y-axis and z-axis. Unit length along x, y, z-axis. So a square, b square, c square into, or length along a square, unit length. Okay, just correct word. 1 minus cos square alpha minus cos square beta minus cos square gamma plus 2 into cos alpha into cos beta into cos gamma. Yes, this is the formula we use to find the volume of one unit cell. This formula is a general formula. It is applicable for cubic, tetragonal, orthorhombic, monoclinic, okay, hexagonal. For any unit cell, you can use this formula to find the volume. Okay, take down. Okay, I'll take one example and I'll show you how to get interplanar distance, okay, for a particular planes, similar planes. Okay, say I'll take orthorhombic crystals. Orthorhombic, right? Crystals are unit cells. Orthorhombic crystals. You know very well, in orthorhombic crystal, A not equal to B not equal to C. Side lengths are not equal, but alpha, beta, gamma all are equal, and it is equal to 90 degree. Okay, observe carefully. First we'll find out the volume. Okay, volume. V is equal to, see, A, B, C are not equal, so you'll get A square into B square into C square. Then alpha, beta, gamma all are 90 degree now. Okay, cos 90, you know very well, cos 0 is 1, cos 90 is 0, 0, 0, this becomes 0. So except 1, everything becomes 0. 1 into this, you'll get A square, B square into C square. Yes, this is the volume of orthorhombic unit cell. Take down. I'm very sorry, actually I made a mistake. Here it is V square, sir. Please put V square. Okay, because here we have V square. This is the formula for V square. So this is V square. Now, what is V then? What is V then? Listen. V square equal to A square into B square into C square. Therefore, V is equal to square root of A square, B square, C square, which is nothing but A into B into C. This is the volume formula for one unit cell of orthorhombic crystal. Okay, take down. Listen. So 1 by d square for HKL plane is equal to 1 by V square. See, we have found out V square. V square is nothing but A square into B square into C square. This is V square into here sin alpha. Alpha value, you know, alpha is 90 degree. Sin 90 degree is 1. Sin 90 degree is 1. So here we get H square, B square, C square. Plus here sin beta also 90 degree. So Sine 90 is 1. So we get k square into c square into a square plus. Then here gamma also 90 degree. So we get L square, a square, b square. Then here we have cos alpha, cos beta, cos values are cos alpha, cos 90 is 0. So this becomes 0, this becomes 0, and this last term also becomes 0. We have only cos. Cos alpha, cos beta is 0. Therefore, we left with only these three terms. Okay. Now what I am going to do, observe carefully, I will multiply this inside. So 1 by d square HKL equal to, I will multiply inside. If I multiply inside, b square, c square, cancel. So I will get h square by a square plus, if I multiply here, a square, c square cancel, you will get k square by b square, and here we will get L square by c square. Yes, this is the formula which gives you the interplanar distance between similar HKL planes in orthorhombic crystals. Okay, take down. Now we'll see how to find interplanar distance between similar planes in cubic crystals. Okay, already we have worked out for orthorhombic crystal. Now I am going to show you how to find interplanar distance for cubic crystal. Listen, for orthorhombic crystal, A not equal to B not equal to C, alpha, beta, gamma are all equal to 90 degree. Okay, this is for orthorhombic. For cubic, alpha, beta, gamma equal to 90 degree. Okay, this is same. But A, B, C are all equal. So, if you see, first I will take the formula for orthorhombic crystal. For orthorhombic crystal, we get the formula as 1 by d square HKL plane is equal to h square by a square plus k square by b square plus L square by c square. Okay, this is the interplanar distance formula for orthorhombic crystal. What is the difference between orthorhombic and cubic? Okay, in orthorhombic, A not equal, B not equal, C, but in cubic they are all equal. So A, B, C are all equal. So what I am going to do, h square by a square, in the place of B also you put a square, because A, B, C are all equal, plus L square by a square. Now all the bases are same, therefore I can write h square plus k square plus L square by a square. This is 1 by d square. Okay, now take the reciprocal. So if you take reciprocal, d square HKL equal to a square by h square plus k square plus L square. Now if you take square root, you will get the interplanar distance between similar HKL planes. Similar HKL planes equal to, if you take square root, you will get a by square root of h square plus k square plus L square. Yes, this is the interplanar distance between two adjacent similar planes in cubic crystals. Okay, take down. And suppose I'll take, for example, I'll take some cubic crystal, and it has some plane, say for example, I'll take 110 plane, some plane, 110 plane. 110 plane means it cuts the x-axis at 1 unit, y-axis at 1 unit, but it is parallel to Z. Now this is the HKL value. Now we need to find out what is the interplanar distance between 110 planes. Okay, I have 110 plane, another 110 plane, another 110 plane, which are all parallel. What is the distance between them? Okay, is equal to, since it is cubic crystal, it is equal to A, where A is the side length of the cube, divided by square root of h square plus k square plus L square. So 1 square plus 1 square plus 0 square. Yes, we get the answer as A by square root of 2. Right? Through X-ray diffraction technique, we can find the interplanar distance experimentally. Through X-ray diffraction method, we can find the interplanar distance experimentally. If you know interplanar distance, you can find the unit cell parameter A. Okay, so this relation is very important because using this you can find the unit cell parameters A, B, C, alpha, beta, gamma, everything we can find. Okay, take note. So we'll discuss tetragonal crystal if you want. Tetragonal crystal. Okay, see, you know very well for orthorhombic crystal, A not equal to B not equal to C, alpha, beta, gamma all are equal and it is equal to 90 degree. Okay, this is for orthorhombic. For tetragonal system, A equal to B but not equal to C, whereas alpha, beta, gamma all are equal and it is equal to 90 degree for tetragonal system. Is this correct? Check it. So for orthorhombic crystal, we got the interplanar distance d1 by d square for the HKL plane equal to h square by a square plus k square by b square plus l square by c square. This is the formula for orthorhombic crystals. Now for tetragonal system, listen, A and B are equal, right? A and B are equal. So I'll put h square by a square plus k square. Instead of B, I can put A itself, A square, but C is different, L square by C square. So I'll take LCM here. I'll take h square plus k square by a square plus L square by C square is the interplanar distance 1 by d square HKL. So by making use of this, we can find the interplanar distance between similar planes, similar parallel planes, okay, in tetragonal crystals, right? So in X-ray diffraction method, the first step is we need to understand how to produce X-rays. I'm not going to discuss right, X-ray production. I'm not going to discuss the experimental methods and all. Okay, you know very well X-ray was first discovered by Röntgen. Okay, and he took a glass tube and he kept some metal target, right, and he created electrons, thermal electrons, fast moving electrons. When the metal target, you take some metal target, when the metal target is bombarded by electrons, okay, X-rays are produced. This is the idea. Okay, you take some metal target and bombard that metal target with the fast moving electrons. Okay, you can produce what is called X-rays. Okay, this is a basic idea. Now listen how we get X-rays. See, if I plot the intensity of this X-rays that is produced versus the wavelength of the X-rays. Listen, if the potential or the potential applied to produce electrons, right, depending upon the potential or the kinetic energy, we can say in the other way, right, we get X-rays, right. So if we use low energy X-rays, right, you will get different wavelength of X-rays produced. See, if we use low energy electrons, we get X-rays of different wavelengths. It will appear like a curve. Okay, we say that it is white X-ray. Often we say that white X-ray or polychromatic X-ray. But when we bombard with a high energy electron, listen, we get X-rays something look like this. We get a small peak, then we get a large peak, then it goes like this. Okay, observe carefully. We get 2 peaks here. These are all X-rays, different X-rays produced, right? And this is the X-ray whose wavelength corresponds to K alpha line or K alpha rays. and this is nothing but K beta rays. This is K beta. Okay, we call these K alpha and K beta as characteristic X-rays. K alpha and K beta, they are called as characteristic X-rays. Characteristic X-rays. Characteristic X-rays are produced only when high energy electrons are used. When you use high energy electrons, yes, along with other X-rays, you have other X-rays also. But apart from these, we get characteristic X-rays of high intensity. In these two, if you compare K alpha and K beta, intensity of I means intensity of K alpha line is much greater compared to K beta. So, for X-ray diffraction studies, we often use, most of the time we use K alpha X-rays. Okay, K alpha X-rays we use, right? We need to filter K beta and other unwanted X-rays. Okay, these are all X-rays having different wavelength. Okay, but we need the X alpha X-ray alone to study the crystal structure. So we need to filter the other X-rays that is produced here. Okay. So what are characteristic X-rays? How to understand this? So you take an atom. In atom we have nucleus at the center. We have K shell. We have L shell. We have M shell. Like that we have different shell K, L, M, N, etc. Now let us assume that we have an electron in the K shell. Okay, we have an electron in the K shell. Now with the fast moving electron I am bombarding this atom. Okay, this electron bombards with the electron present in the K shell, suppose. By bombardment, if this electron comes out, okay, this electron hitting this electron, therefore this electron is moved away, right, from the K shell. Now what will happen? It creates a vacancy in the K shell. This electron, after hitting, this electron also will go away. Now we lost one electron in the K shell. Now what will happen is that, listen, this is actually the electron in the K shell has lower energy. So now this electron removed an electron from the lower energy shell. Now in order to stabilize the system, what will happen? Electron from the L shell, electron from the M shell, they start to jump out to make the system stable. So electron may come from L shell to K. When the electron jumps from L to K, listen, this is higher energy electron. It is jumping to the lower level. When it jumps to the lower level, it releases a radiation called K alpha radiation, because the electron moves to K shell, so it is called K alpha radiation. Okay, if this electron jumps here to fill the vacancy, this electron, listen, this is also jumping to K shell, K, but from the mth shell, so it is called K beta line, K beta radiation. So when electrons bombard with the metal target, it will remove electron from the inner shells. Okay, whenever K shell electrons are removed, suppose K shell electrons are removed, then what will happen? Electrons from the higher energy level, they starts to jump to the K shell. When L shell electron jumps to K, you will get X-rays called K alpha X-rays. When M shell electron jumps to K, we get X-rays called K beta X-rays. Is this clear to all? Listen, among the K alpha and K beta, K alpha X-ray has high intensity because the probability of transition is very high. Okay. So since K alpha has high intensity, we use K alpha X-rays to study the crystal structure. Okay, so we don't want K beta. So what to do? We have to filter off K beta and other X-rays. Okay, take 2. See, these are the K alpha rays and K beta X rays produced from different targets. Okay, chromium, iron, cobalt, copper, molybdenum. You know very well, for many X-ray diffraction studies, right, we often use copper target. Okay, so remember the value of K alpha. Don't worry about what K beta, because we are going to filter K beta lines. We want only K alpha because K alpha has high intensity. Okay, take 2. So to filter K beta rays, K beta X rays and other X rays, we use filters. Okay, what filter we use? Listen, I'll write the target here, target and the filter. Okay, listen, target may be molybdenum, target may be copper, target may be cobalt, target may be iron, target may be chromium. Observe carefully: molybdenum, copper, cobalt, iron, chromium. Okay, for this, what filter we are supposed to use? Listen, you just tell me in the periodic table which element will come before molybdenum. Anyone? Molybdenum.
Neodymium, sir.
Molybdenum.
Tungsten.
Molybdenum is present in chromium group, right? Chromium, molybdenum, tungsten, right? Chromium, molybdenum, tungsten. Before chromium, which element we have? Chromium, vanadium, right?
Yes, sir.
In the vanadium group, below vanadium, what's the next element?
Neodymium, sir.
No, your answer is wrong. Correct.
Sir.
Listen, in the periodic table, before copper, we have nickel. So nickel is supposed to be used to filter K beta radiations and other radiations of copper. Then if you use cobalt as target, before cobalt we have iron. We should use iron as the filter. If we use iron as target, before iron we have manganese. So manganese is supposed to be used as the filter. For chromium, okay, before chromium we have vanadium, right? We should use vanadium as the filter. For molybdenum, we use zirconium. Take note. These are all the filters we use to filter off K beta X-rays and other X-rays. Okay, take note. See, for the X-rays used for crystal structure study. Okay, what's the range of X-ray we use? We use from 0.5 to 2.5, and remember all are K alpha radiations because K alpha radiation have high intensity. Okay, take note. Now